Hey guys, and welcome back to this episode of Curious Scientist. In this video, we will derive Schrodinger's equation. This is an incredibly powerful tool, which is still not properly understood. It defines the interactions of particles on a microscopic scale, a scale so small that our normal intuitions of classical mechanics no longer apply. Let k equal 2 pi by lambda, with lambda as defined in the de Broglie relationship. This means that the momentum of our particle is equal to h bar times by k. Let's also write down the wave equation. This says that for an equation governed by this differential equation here, the second derivative of phi with respect to position equals minus k squared phi. And this has solutions such that phi of x and t is equal to phi naught times by e to the I kx minus omega t, where omega is the speed of the wave times by our value for k here. I've used the complex form here because it is a more general equation for the wave. Now, let's consider energy, which we can write down in its classical expression. E equals k plus v. This is tantamount to saying that the total energy of a system is equal to the kinetic energy plus the potential energy. We can further specify this by saying that the total energy is equal to half mv squared plus the potential energy. However, we want things in terms of momentum rather than velocity, so we can rewrite the kinetic energy as p squared upon 2m equals p squared upon 2m plus v. And this is what the total energy in each case is equal to. So let's rearrange this in terms of p squared. P squared equals 2m times by e minus v. And now, because we know that p equals h bar times by k, we can say that k squared is equal to 2m over h bar squared times by e minus v. And to get to this expression, we have used this equation here, and we have plugged it in to this equation here, and then simply divided by h bar squared. Now, we can substitute this back into the wave equation, because we have two expressions for k squared. One is here, and one is here. This yields that d squared phi by dx squared equals minus 2m over h bar squared e minus v of phi. Or equally, and this is perhaps in the more familiar form, that minus h bar squared over 2m d squared phi by dx squared plus v of phi equals e of phi. Now this is the time-independent version of the Schrodinger equation, but we want the more general time-dependent equation. And this can be derived by noting that the energy of a particle is equal to hf, or h bar omega. Let's write that down. The energy of a particle is equal to h bar omega. Now this is just using the Planck relationship, that E equals hf. Thus, for a plane wave, whose equation is of this form here, we can say that d phi by dt, or the rate of change of the wave function with respect to time, is equal to minus I omega phi. Now rearranging this gives us the following form. First we divide by minus I. 1 over minus I d phi by dt equals omega phi. Next, we multiply by h bar. And with a little bit of simplifying of the 1 over minus I expression, which is itself equal to I, we get the following. We get that I, h bar, d phi by dt is equal to h bar omega phi. But we already have an expression for h bar omega. We know that this is equal to the energy of the particle. So we can rewrite this in the following form. I h bar d phi by dt is equal to E phi. And now we can substitute this back into the equation to get the time-dependent Schrodinger equation. So going from the time-independent Schrodinger equation here, time-independent, we can notice that the following two terms are the same. We have E phi here, and we also have E phi here down the bottom, and we can simply set these equal to each other. And this yields the following. It says that minus h bar squared over 2m d squared phi by dx squared plus v of phi is equal to I h bar d phi by dt. And now this is the time-dependent Schrodinger equation. The modulus square of the wave function is a measure of the probability of a particle being at a particular location, not the wave function itself. That is tantamount to saying the following. So to reiterate, the modulus squared of the wave function is a measure of the probability of a particle being at a location between x and x plus dx. This is how we relate the Schrodinger equation to the real world, and it produces profound implications for situations such as the double slit experiment. This is just one of the many applications of the Schrodinger equation. You've been listening to a Curious Scientist video. If you liked it, don't forget to hit that subscribe button so that you can get new videos just like this every week.